Oh, hello, and welcome to you who managed to come to this almost last session in the furthest room. This talk is going to be a bit different from, I think, most others during the conference, because unlike others, I'm going to focus on something which is at the root of what we deploy when we are creating sites. Site reliability engineering is about sites, and at some point, sites are all based on software. And here we are going to talk about a technique which can be used to impact the reliability of software itself and not the way you deploy it. Because if you reflect on, if you reflect on the talks we've been seeing for these 2 days, they're mostly talking about observing running software or deploying it. Here we are talking about something that is about how to better write software which will scale for concurrent operation. So first, who am I? I'm a consultant. I don't have a product to sell, unlike any others in this conference. And I work mostly for large companies, mostly in France, and some even in the US, like Medicare and a few others. So what's TLA? TLA is, first, it's a language. It's something about formal logic. It's created by a scientist who's well known in computer science. It's Leslie Lamport, was the guy who created LaTeX, if you've ever used LaTeX to typeset some documents. And actually, TLA Plus started as just an extension of LaTeX, just to typeset formulas on formal logic. And then at some point, someone had the idea, since we now have this language to typeset these equations, could we check them? And that's how it came to be. Technically, it's based on the Zermelo-Franker set theory with the axiom of choice. You probably don't want to care about that, but it has a solid grounding in mathematical theory. And it focuses not on how you write code, but about how the whole system you are deploying operates. Then that can mean a system can be a single component with its own internal threading, say a Go program with its Go routines or threads in Java or whatever. But you could also apply that to model a number of agents operating. Say you have, for example, a cluster of microservices. You can define expectations between them and then decide on processing, and that's how it integrates with the whole SRE discipline. Here's the creator. As you can see, that's typical scientist. It's his own photo in the course about TLA. Anyway, why do you want to use that? Because you are going to work on the description of the problem and the system instead of the code. You are going to find design flows before your team start to develop. It enables checking algorithms, checking network protocols, checking anything about the way various components interoperate. And in that way, it goes in front of the development. It's a complement to traditional testing. For example, if you have some code, you are building a POC, say, for example, you will do unit tests, and these tests will check the cases you have thought about defining. Even if you go one step further, first tests will only extend the cases you have already defined, and they will find a few other cases, but they will not go beyond what you already defined. And if you think about economics, the most expensive bugs are the ones which happen after you have already done the work because you skipped the errors while you were still doing the design. And these are the most costly. And if you can get the errors by analyzing your system before you worry about the code itself, you can save big. And that's the promise here. So who uses that? The most notable references are with the hyperscalers. Amazon was an early adopter with S3. They created a whole model, and that they published this paper, put the link in the slides, which they attribute a lot of the reliability of S3 to their ability to create a formal model which found a lot of errors and enabled them to fix them, whereas nothing in their test suite ever found those. And then, of course, when Microsoft decided to clone MongoDB for their own use and create Cosmos DB, they used it to replicate the protocol and ensure that all the behaviors were the same as those of MongoDB, even using a clean room engineering to deploy it. Closer to me, because I do a lot of work on Kafka, the Kafka authors started to work with TLA when they were developing the new replication protocol called KRaft. And since it was proved to find other errors again while still on the design board about the protocol, they started using it on many other KIPs, which are the Kafka improvement protocol requests. And so you have a lot of work done with TLA in the Kafka space. All these papers, of course, focus on how it worked well and how it saved them months of debugging and prevented outages and so on. I have a return on experience at the end, which will maybe temperate this a bit, but it's globally, here's the value proposition. If you fix a bug while you are designing, you stop early here on the bad path, and it costs little. If you find the bug with tests, for example, or using tests, unit tests, first testing, it costs more, but it's still not huge. And if you have to fix something once it's in production, it's of course much more expensive. And TLA Plus tries to find the bugs that we would have missed when doing testing, because when you build tests, you can't avoid it. You try to focus on the happy path, and then, okay, this can fail. I need also to test that sad path, and that sad path, and that sad path. But you may not be able to think of all the sad paths, especially when you are not doing sequential code, because the value here is about the concurrency. Because we humans tend to be pro at representing things in our minds when things are moving in time-space at different rates. How does that work? Basically, it's an extension of the traditional logic you have studied in high school and in college and maybe later. Basically, when you start doing traditional logic, there's this assertion that whatever the proposition, it's equal to itself. And now, we have to question that. How can it not be true? The question, is it always true? And the always should give you an idea. What does happen when you perform the evaluations of this property at two different instants in times? Because in the real world, where you are evaluating things using code, you can never be exactly at the same instant doing the evaluation. And so consider a property like this one. The process is running now. You run it at some point, and you get a result. And then you run it at another point, and you are likely to get another result. And it's still the same proposition. But the distinction is that time has been introduced to it. So traditional logic evaluates everything in an instant, an abstract instant which is never defined. And temporal logic, like temporal logic of actions, which is the name of TLA, adds that temporal dimension to everything you are doing. And there's this notion that a predicate, a property, can be evaluated at different times, and all the instances at which a system exists are evaluated over all the successive instances of time, which is seen to be a granular series. It's divided in smaller events, like the minimal time duration, which is Planck time, for example. And you evaluate all the instances from the instant the system starts to when it ends at that granularity, which means most of the time nothing will be happening. And when you evaluate a given property, you do it at one point, and then you will compare it with how the system evaluates at another time point later. And this is what you express with TLA. There are various ways to perform temporal logics. Temporal logic in TLA, the linear temporal logic, is the simplest one. It's already complicated enough, in my opinion, so you can look at the others, but it's even more abstract. Let's consider a simple example. Here you have a light switch, on-off. You have two states, light is off, light is on, and you can turn it off or turn it on. That's a finite state machine, very minimal one, and you can express it. In TLA, it looks like this. You define a variable which is light. You say initially, I define the initial state as being one where the light is off, and this is the only condition we have, the only predicate. One action can be light is off and light prime, which is the next step at some point in time will be on, and conversely, turn off is the opposite. And we have this next transition, which is defined as the logical union of both. And the fact that we have this next describes all the operations which can actually happen. Because start at the initial state with light off, you can see that what can happen is either turn on and turn off, and you see that turn off does not apply because light is not on, so your automated finite state machine has to move at this point or remain in place. And this defines the only path you can take. You could also write it with a single action. And one thing to note when you do that is that to add a single action, you have to add one more bit of information, and that is to describe where you are currently. And it's a general trend that you can reduce the number of actions in your machines by expanding the size of the state vector. Now we have this first concept. The actions are the steps which can be taken from one state to another, and they are described using the preconditions, meaning how is the system when it starts, the variables without the prime, and how is it when the transaction has ended, and it's defined with the prime. These are the precondition and the post-conditions, as I explained here. Let's go with another bit more complex example. This is traffic lights. Traffic lights usually go green, orange, red, and again. So you have this circle of the three colors. You can model that pretty much the same way. It's just like the switch, just a bit more involved. I won't go into details, we don't have much time, but notation is the same. It's either red and then light prime will be green, and so on. So you describe what happens the way the system moves. And then you can have something which are more complex. Consider you have made a single model of this system running, and now you are trying to look at Spanish traffic lights, which go red, yellow, green, yellow, red. They are not running in a circle. So you try to apply that same model, and all of a sudden you notice that there's a problem. Sure, you can do the whole loop across the three states, but you could also go green, yellow, and you don't want that. This would not be fair. And you can assert that with the language itself. And you add another condition, which is the unchanged, saying that didn't change. Again, we add one more bit to the condition. And now you have restored your cycle. Same idea of reduce the number of actions, extend the state, or go the other way. You have to choose to describe systems. And that allows you to define two kinds of properties. You can say safety properties say that something needs to be respected. For example, in our traffic light example, the traffic light is never both red and green. That would be a definite flow, and the machine does not allow it. This is a safety property. And you have another property, which would apply to this Spanish light example, saying at some point the light will be green. And that's interesting to have too, but you can't have that kind of property if you don't start to use time. And these are called the liveness property, meaning the system won't stay stuck without going through its other states. And once we have described this, we have a model. Now we need to do something with it, and this is what model checkers do. There are several model checkers, and the model checkers examine the transitions, the actions, and the states defined by the model, and they run through exhaustively all the cases that can exist within the system by squashing the constant time that the states which remain the same to remain in a finite number of cases. You have mostly two model checkers available, TLC, which is provided with TLA Plus, and some other third-party models. And the idea is to define this model will have some invariants, some properties which will always be true, and the model will go through all the states, all of them exhaustively, and verify that they always hold. And if they don't, you will have found an error. For example, for the Spanish lights here, which is 30 lines, this is how you look. You can write your specification. You say the initial state, next state. The invariant is the type is always OK. And what does the type say? It says OK. It's the third block. It says it's defined as either the light is one of the colors and it's going to green is a Boolean. This is the only criteria that define that your system is good, and also it does not deadlock, which is an optional state check you can have. You can run this. It finds the 4 states, and it finishes in less than 1 second, obviously. I will skip the syntax just to give you an idea. It defines states, variables, and examples, and it's based on just 6 symbols. One is the assignment, another is the implication, pretty much like the then in logic, the and conjunction, the or conjunction, the equality for values, and the membership in a set. And this is where the Zermelo-Frankel set theory comes in, because this is how sets are defined. And the axiom of choice is needed to ensure some consistency properties about sets. Prime variables, as I've said, describe what happens after one quantum of time has elapsed. And this is how you move. And finally, when you define your specification, you have the last line at the bottom right here. The specification is the union of the init state and the infinite sequence of all the next events which can happen to the light property. This is a specification, and that's what your code will be able to check. Stuttering step is the notion that in most cases, the system will stand and do nothing. If you think of a traffic light, for example, most of the time it's just waiting. It's not constantly going through all its states at Planck speed, of course. So all systems have to support that. And formula are of three kinds. A property will always be true or eventually be true, or if one property happens, then another will happen. These are the three types of rules that you can define. For example, you can always say that if the light is red, at some point it will be green. This is a liveness property. Specifications are just the way you codify what properties will exist, the initial conditions, different variables. Basically, this is the configuration you are going to push into your model to validate it. And you can define either init and next, or completely a specification yourself. Here you have an example of a mutual exclusion, like the mutex in Go. And that already with just two conditions, you have 8 states. That explodes fast. But now look at the same state space with just 3 variables. 3 variables, no, we would expect just 8 states. And no, here are all the states you can get with just 3 variables in a mutual exclusion. I would bet that no team would actually write the unit tests for all these cases on their own. They wouldn't think of all of them. Yet the model has enumerated all the cases because it has this formal definition of the system, and it will go through all of them. And of course, that has a cost. It's not really exponential that we are in log space, and it has a small way to, it decreases a bit over time, but it still looks very much exponential if you look at the blue curve. So it's very costly to run. For example, here at some point I started running my tests. I think you can see where I starting the tests. This is the use on my machine. And so the model makes use of all the cores you can give it, and you can actually spread it over multiple instances. You will usually use spot instances to minimize costs with that. Here's what a mutex looked like, 50 lines to define that, and you can check it. Anyway, there's a complete separate language which builds on top of TLA+, which looks like a programming language, but we don't have time to talk about it, and actually I would not advise doing it. I started by trying to use that, and I think it's actually more complexity than it's worth. Let's finish with how that is used in practice. When do you want to use that? And first, you want to use it for concurrent systems. If you are doing sequential code, there's no value in having all that complexity and learning all the tools and the syntax and everything. But if you are writing the next database engine, which has to be concurrent, or a DNS service like Azure did, because the DNS is notoriously hard to do right and insecure, a protocol like Paxos, which is something quite complex to synchronize concurrent systems, this is valuable here. Also, since that has a cost which is initially hard to justify, you want to do this for critical systems. For example, if you are doing content management, you usually have no reason to care about that. If you have to do a live support system, that's another story. Then it makes sense to try to be sure about your design. And you can do this either in the early design to ensure that you can actually do the system concurrently, or when you have to evolve a system which is already breaking under its own weight and is too complex, you can take a bit, model that bit, isolate it, and make it safer, and then move on to the next. Pretty much the same way that you do refactoring in legacy code. You isolate a part, you make it safe by adding test coverage, and you move to the next. Same approach. This is how it was added to Kafka, actually. How does it work with your development workflow? The best idea is to do that when you are still writing the specifications. It does not mean you have to have a full design of your system, but for any component, before you start working on that critical concurrent component, you do it very early in the design. And then you check your models with TLC or whatever. You cannot generate code, which is still an area of research. There are projects to do that. And then you can use that for documentation. You can generate the graphs from your state machines. You can generate the renderings. That provides the documentation, which can be useful. And it can also be used to discuss within the architects, between the architects, the developer, the various stakeholders. It provides a kind of unified language, pretty much like you have the domain language when you're doing DDD. Have something which is not ambiguous about what we are trying to do. And it's good to train new team members to arrive, because I would say no team has people arriving who are trained in this kind of logic, so it's good to do it as early as possible. There are a lot of tools provided in a single jar, which you can just unpack, and you will get a number of commands which can run on your machines. The biggest change, which was finally published 2 days ago in version 1.8, is you now have a REPL, Read Evaluate, which is basically an interpreter for TLA. You can run operations just from the CLI. You run TLA, and you can start typing in and getting results, like what you would do with any interpreter. Lots of various tools. There's even a separate symbolic model, which is heavily subsidized by Microsoft, for example, to go with other solvers. Once you have defined the model in TLA, you can export the model and have it checked symbolically instead of by going through exhaustive check, because you understand quite well that you can have an explosion of combinatorials with the state space, and doing through all the cases like TLC does is not livable for large systems. And Microsoft, for example, has large systems, and so they need to have symbolic resolution instead of using exhaustive search. But it's still using the TLA plus format at the root. And something else which is developed by INRIA, the French Research Institute, is the proof system, which tries to do safety proofs on the TLA code, not liveness, but safety only. There's even a profiler showing how much time you spend in each state. And I would recommend you do that. Start small. Start with a single component. Don't be too ambitious, or you will be burnt out. I'm currently working at a large scale-up, and the first attempts to use TLA a couple of years ago failed because they were too ambitious. This last try we did this year succeeded because it was small and targeted to a very critical, very fast concurrent component. If you look at the course, there's this little secret. The dirty secret of formal methods is that the only way to make them school is to use state machines, and that's usually a disappointment. You have been thinking of all these ways of defining your model, and that in the end, when you have enough states, the only thing you can do is do a finite state machine and define the states, and your model starts to make sense, and you can code it, because that still doesn't define your code. Couple of words about GenAI. That has been my biggest disappointment, actually. I've been trying to use all the agents available, and no one understands anything at all about TLA. They generate incorrect syntax. The Pascal language, which is on top, has two different syntaxes, and none of the agents know the difference. They will claim to do one while writing it in the other one and mix in one of the... It's a complete mess. I think at some point it will improve, but not yet. And finally, what are the lessons I learned from this? Because this was the first time I did such a project this year. And although I had my model done, my code still broke. What the heck? The part that I had modeled proved to be bug-free, actually. It's been in production for 6 months. At this point, there's not a single bug found in it, which is very nice. This was the goal. However, the package which had been created on top of this model was not bug-free, because I had forgotten that at some point you need to enter the code and start to enter the model, and there was a bug there. And I have forgotten to do what happens after the end. This is the last slide, don't worry. Actually, there was a bug after the end of the model. So the lesson here, verify what your code does before you enter your model and after you leave it. Don't stop after that first component. And if you have dependencies, the issue I had with the code implementing the model was APM component. Turns out it had a bug. And of course, that crashed, although the model itself was fine. So if you have dependencies, you should put them in the model too. And as I explained in the beginning of the presentation, sometimes you can save the number of states by just adding a couple of bits of information in your system state. And these are all the insights I have to give for now. Thank you.